Hello and good morning. What a beautiful, wonderful day. I am excited and or happy for two reasons. Number one, this is the last day before spring break for our school. I am thrilled, and it's supposed to be 70 degrees today. Oh, fantastic. Number two, we are starting Module 5, which is the very last unit we do before we start reviewing for finals. So let's just jump right in. We are going to start with Unit 5, Lesson 1. This is an intro to probability. Okay, a lot of this stuff should be really familiar to you. Some stuff may be new, but let's dive right in. Let's first discuss the basic definition of a probability. Okay, in terms of a fraction, a probability really is, it's the number of desired outcomes over the number of total outcomes. Okay? It's the number of desired outcomes over the number of total possible outcomes. All right? And when it comes to probabilities, those fractions can be turned into decimals. All probabilities, whether they're fraction or decimals, should be between 0 and 1. 1.00, yeah, okay, board is stroking out, representing 100%, and 0.00 representing 0%. Everything in life has a chance between 0 and 100%. I'm not talking about growth and decay, like your money can grow 300%. I'm talking about probabilities. All right? And let's begin with the basics. Okay, these are things we always start with. All right, a coin and one dice, which we call a die, which took me a while to get used to, but hey, that's proper English, correct? Correctamundo. So, the probability of landing on heads from flipping a coin. Well, my desired outcome, I only have one option. Heads, right? The total number of possible outcomes when flipping a coin are 2. I can either land on tails or heads. So it is desired over total, 1/2. Or if we wanted that in decimal, it's 0.50. If they said what is the percent, which they don't often do that, obviously 0.50 would be you have a 50% chance. Okay, but it would typically be 1/2 or 0.50 unless they specifically ask for percent. Okay, let's take a look at our next example. The probability of rolling an odd number on a 6-sided die. All right, well, my desired outcome, if I want odd, there are 3 of them, correct? 1, 3, yep, that's okay. And 5 are all odds. Sorry about that, a little dyslexia kicking in. And the total number of outcomes, there are 6. I can have 1, 2, 3, 4, 5, or 6. So the number desired over the total. 3 out of 6 chance of landing on an odd number when I roll the die, which again is 0.50. Basic, simple, but I think they really explain or show how probabilities work. Okay, let's bring in a little bit of Algebra 2 to everything we know from Algebra 1 when it comes to probabilities. All right, we have 2 basic types of probabilities, theoretical and empirical probability. Now, they mean 2 different things. Let's define what they are first, okay? So when we talk about theoretical probability, we really can say, well, we don't actually have to run an experiment to determine what the probability of the event might be, okay? I can figure out what the probability is just on my mindset alone, my theory. I can, and that's why it's called theoretical. In theory, okay? In theory, meaning I don't really have to run the event. I can kind of just mathematically assume, using logic and common sense, come up with a guess on what we may or may not end up with. All right? That is theoretical probability. Empirical probability is not theory at all. You actually need to run the experiment and pull your odds from that. So, theoretical, okay, let me go back here. Theoretical is in theory, right? Empirical with the E, you actually need to run the event or run the experiment. Okay? And I have two examples below here, and I will kind of explain through examples what these really do mean. Okay? This first one here. Let's do this first one. This is theoretical. We flip a coin 4 times. Okay? What is the theoretical probability of a coin landing on heads on the next flip? All right? I don't need to flip a coin 50 times to figure out that, well, anytime that I flip a coin, my desired outcome, that's heads. Total outcome, I can have tails or heads, right? That's still 1 out of 2. We just did that. That is a 0.50 probability, 1 out of 2. That is in theory. Every time I flip a coin, it has a 50-50 shot of being heads or tails. Theoretical probability. I don't have to flip that coin to know it. Let's talk about empirical probability. If we flip a coin 4 times and we actually record the data for that, and the first time it lands on heads, the second time tails, the third time heads, and the fourth time heads. What is the empirical probability of the coin landing on heads on the next flip? This is not theory anymore. We are actually going to use our data. Okay, we had our desired output of heads, we had 3 times. 1, 2, 3 times. Total, we flipped the coin a total of 4 times. So empirical probability tells me the coin will land on heads, a 3 out of 4 chance, or a 0.75 chance. All right. All right, let's take a look at an example here. A survey was done by a marketing company to determine which of the 3 sodas was preferred by people in a blind taste test. The results are shown below. So this is nice. We have all of our data in this table right here. Here's soda A. Wow. Oh my God, it just stroked out on me. Look at, oh, you don't see how far off that is. So, wow. Let me pause this and realign it. Okay, let's start this over. Here is our data. Good. And here's soda A, soda B, and soda C. And the number of people that prefer that. This is a total of all the people if I add them. Okay? So, let's do some math. Find the empirical probability, that means we're using our data, that a person selected at random from this group would prefer soda B. Okay? Express your answer as a fraction and as a decimal accurate to 2 decimal places. So, they want to know, out of all these people, these is the total, okay? How many people prefer B? These are the people that prefer B. All right, so my fraction is literally 24 out of the 53 people they interviewed or asked preferred soda B. So now there's our fraction. Good. They also want it as a decimal to 2 decimal places. And let me get out of this function I was just working on. We take 24, we divide it by 53. Kadoosh. And I would call that 0.45. Okay? They want it to 2 decimal places. Here's the second decimal place. I look at the third one to see if it's rounded. That is a 4 or lower, meaning it's less than 5. Approximately 0.45. Easy. All right, easy. Now, let's get this out of here. The second question, is there three? No, there's only two. Find the empirical probability that a person selected at random from this group would not prefer soda A. Again, express your answer as a fraction and then a decimal to 2 decimal places. All right? If I say, okay, here are the people that like soda A, but notice it says that would not prefer A, which means which two groups do not? Obviously, the people who like B don't want A, and the people who like C don't want A. So basically, I don't want A. Who are the people who don't want A? It's all these people right here. 24 and 11 give me 35. This totals 35 out of my 53 people who would not prefer A. They either prefer B or C. So 35 out of 53. And again, I go to my calculator because I have one, and I do 35 divided by 53. 0.66. This is approximately equal to 0.66. There you go. You know what? Working with a table with numbers in it, so easy, because the numbers are right there for you, right in front of your face. Here's something that will pop up every once in a while, and it is the complement, which means not. Okay? It is the complement. It is the probability of something not happening. Okay? Coffee is so good. Now, if the probability that it will rain tomorrow is 20%, what is the probability that it will not rain tomorrow? All right. So this, again, is just basic. We're not going to go that far into it. If we are talking about complement, which is what we are talking about right now, the word not, I take 1 and subtract the probability of the event actually happening. Okay? I take 1 and I subtract the probability of the event happening. Now, we'll get into this in a moment, but the probability that it will rain is 20%. So I say the probability that it will rain, I'll use R for rain, is 0.20 because we like to use decimals. All right? If I want to figure out the complement, which sometimes they use this tilde, right? Like that. Or sometimes they put probability that it doesn't rain in like that. All right? I'm going to take the number 1, and I'm going to subtract the probability of it raining. Now, common sense should tell you, if there's a 20% chance that it does rain, there's an 80% chance that it will not rain. Okay? So if I use this math here, I take 1, subtract my 0.20, and I get 0.80, which is 80%. All right? Just a little bit of common sense wrapped in some mathematics. Now let's actually start to talk about some symbols that you'll see in probability and give some explanations and names for them, all right? Well, we just discussed with the rain problem what P of a symbol means. This is the probability of event A happening, all right? That's what that means. If they say P of A, that's the probability of event A, whatever it means, whatever A represents, that's the probability of A. Okay? This next symbol here, okay? It's like this upside down U. That is the intersection. They call that an intersection. Yep, there's an I there. Intersection of A and B, okay? Now, this means that they both need to happen, the intersection of A and B, all right? So this is really the probability of both A and, yep, that's okay. I put the B there first, and B happening, both of them. What I like to do is if I draw an intersection, let's say this is street A, right here. It's going north and south. And street B is going east and west. Okay, so street B. Where's the intersection? It's right here. It's where they both happen at the same time. You are on the corner of A and you're not on A only, you're not on B only. You're on A and B. Okay? This location would be just B. This location would be just A. But this location right here is both A and B. That's why it's really called the intersection. Okay? So let me get rid of that. Bang. Now, here's a little tidbit. Sometimes in a problem, they will tell you the probability of A and B happening is 0.40, whatever. But sometimes they only give you a number to represent the probability of A, and then they give you a separate number to represent the probability of B, okay? For intersection, that's a symbol here, okay, which is and, both happening, okay? You would multiply A, the numbers, A and the number of B together to get it, okay? If you were given two separate values, one representing A and one representing B, you would multiply them. So it's the probability of A times the probability of B. All right? Sometimes you're giving them separately, you got to multiply them. Sometimes you're not. Sometimes in the problem, they actually give you the probability of A and B is this. Okay? So just be sharp. Well, this next one, this is a right side up U. Okay? This is the union. And, you know, that's how I always remember the U is the union of A and B. Okay? Now, the explanation is this is the probability of A, but it's here it has both A and B for intersection. But this is the probability of A or B happening. It is not both. It's one or the other happening. All right? And think about it this way. Intersection, I actually gave you an intersection as an example, okay? For union, when you ever been to a wedding where they say the holy union, matrimony, the union of these two people that bring them together, union represents marriage. So if we have a female, sorry, she's wearing a skirt. Here is a male. He's levitating above the ground because he's so happy. But anyways, these are all the things that she owns. These are all her personal items that she owns. These are all the personal items that he owns. When you get married, guess what? They're all both of them. You include everything, okay? And that's what union does, okay? You include everything, all right? You don't just pick the things that, you know, overlap like an intersection and everything else doesn't count. This, everything is now one, all right? And that's what union is. So, in a situation where there's a word problem, maybe they say the union, the probability of A, U, B, or they might say the probability of A or B happening is this. But sometimes they'll give you A and B separately. Now, like intersection, if they gave us to them separately, we had to multiply them, didn't we? But for union, if they give them to you separately, that means or, right? That means you would add the probability of A and the probability of B to get it. If you were given these things separate, you would say probability of A plus the probability of B. Okay? Or would be to multiply, and would be, or would be to add, or is add, and is multiply. And a lot of people get confused with that because they think and means multiply. On word problems, and means multiply. Not for probabilities. Okay, and means multiply. It's not adding. Okay? So, this last note here I want to show you, let me get this out of the way, is the following. All right? If I want to figure out P of A with a union of B, I can take, all right, I can take A plus B, but I want to take out the intersection. And why is that? Because, and I like to do this with highlighters. Let's say this is the probability of A. We're going to bring in a Venn diagram here. This is the probability of A. Okay? And now let's say this is the probability of B. All right? B, A, that's fine. Let's say that there are, I don't know, 10 kids in here. And let's say that there are, I don't know, 12 kids in here. Okay? There's a total of 22 kids. Okay? So there should be a total of 22 kids in here. Okay? Now let's say out of my 12, which are in probability B, let's say 9 are here and 3 are in both. Okay? Which means I'd have 7 here. So my 7 and my 3 would give me my 10, right? My 9 and my 3 would give me my 12. How come I want to subtract the intersection? Because I can't take this and count it as twice. All right? I can't take that and count it as twice. My 10 and 12 here is going to throw you off. How many kids do I have here total? If I put these numbers here, I have 7, 9, and 3. I actually have 19, not 22. Okay? If I take this out and count the 3 here, and I take this out and count the 3 here as well, now I'm counting the 3 twice. I can't double these kids here. If I had 3 children that were taking 2 sports, I don't count them as 6 children. I only count them as 3 children. Okay? I would only have 19 here. So you see how that 22 that came into play would totally throw you off? You need to subtract whatever the middle is. So let's go back to our 10 and 12. Let's take our 10, which is 7 and 3, and add our 12, which is 9 and 3. That gives us 22. But actually, we only have 19. So you see this 3 here? I subtract the 3 to give us 19. If you didn't get that right now, don't worry about it. But that equation takes care of everything, okay? And if you want, pause and rewind it just to hear it again a second time. And here we go. Speaking of Venn diagrams, okay, that's what we're going to have here. I'm going to explain union and intersection. I think I just did explain union. But for 2 sets A and B, their union and their intersection and are given by the following diagrams. Now, a Venn diagram normally is a box out here in case there are some people that aren't in the 2 groups here. And I keep on referring to people in groups because that's pretty much what it is, or things or tests or whatever. But if I want A or B, I want all the people that are either right here, right in here, or the people that are in here, but I don't want to count these people twice. Okay? So when I talk about intersection, I actually want this whole shaded area of the circle. I want the shaded area of all the circles. Okay? I just don't want to double count the middle portion. All right? So union includes everything in the circles. Now, and I'm going to create 2 circles here again. When it comes to intersection, I only want in between where they overlap. The things that do both, or the people that are in 2 sports or 2 classes or whatever. I only want that middle overlap. Okay? That is intersection. All right, and this will be our last problem because the next couple of pages on the home packet are homework. So consider the spinner shown below that has been divided into 8 equally sized sectors of a circle. The spinner is spun once. Okay, let A be the event of the spinner landing on an even number, and let B represent the event of the spinner landing on a prime number. Oh, you better know your prime numbers. So the probability of A. Well, let's take a look at the even numbers. 1, 2, 3. There are 4 even numbers out of 8 possible outcomes because I can go 1 through 8 here. All right. So that probability is 4 out of 8 or 0.5. 50 if you will. Now the probability of the spinner landing on a prime number. Okay. 1 is not a prime number. 2, 3, 5, and 7. Again, there are 4 out of 8, which is 0.50. If you're like Visca, how come 1 is not a prime number? I thought any number that you multiply 1 times itself, and that's the only way, like 1 times 3. That's the only way you get to 3. That's why it's a prime number. The only way you get to 1 is 1 times 1. By definition, a prime number is, the only 2 factors are 1 and itself. So you say that counts here, but the definition also states that they need to be 2 different, distinct numbers, 1 and itself. 1 and itself, and they need to be different numbers. 1 and 3 are different. 1 and itself, and they need to be different numbers. These are the same number. That's why 1 is not a prime. Okay? I shouldn't have had to explain that, but hey, I did. All right, so what's the probability of landing on A intersection B? So that's A and B, the probability of A and B. So it's even and it's prime. Well, I mean, we can use math, but I can also just figure this out. Let's highlight the even numbers, okay? The even numbers are 2, 4, 6, 8. Now, out of those even numbers, which ones are prime? 2. That's the only prime out of the evens. So which one satisfies both? Only one value out of the 8 is even and prime. So that's 1 out of 8. If we wanted to use math, okay, and that is 0.125. But if I wanted to use math, I would take the probability of evens, which is 4 out of 8, and multiply it. No, this is intersection. I would have to, would I add? And? No, and is multiplication. And I would multiply it. See, that's what you really got to think. We're so used to saying add for and. It is not. And I multiply it by the probability of a prime number, which I get 16 out of 64. Okay? But here's the problem. 4 goes into both of those, 4, and oh my God, 16, which is 1, and let's reduce this. Okay? I get 1/4. So why does that not work? Because we need to take out duplicates. Okay? We need to take out duplicates. So you can see how this thing can turn into a giant mess and an incorrect answer when you just have a visual. Okay? You need to take out duplicates. So the only way I would ever use this, okay, the only way I would ever use that is if they told me the probability of A was 0.6 and the probability of B was like 0.3. Then you multiply them to find out P and B. That's the only way. If you're giving a visual with a picture or numbers, it is more accurate to do this. Okay, this will be wrong. All right. Last but not least, or A or B. Okay, so let's go back and figure out. I'm going to erase this right now. Let's go back and figure out. We want either even numbers, 2, 4, 6, 8, or prime numbers, 2, 3, 5, 7. Okay, that is 7 out of the 8. Okay, that is 7 out of our 8. Done. Now, what I'm going to do here is I'm not going to show you the addition for or whatever. I'm going to show you the probability of A, okay, plus the probability of B, minus the probability of A and B. This one is a gem. This should work, okay? The other ones don't stand alone, but this one should work, especially in word problems. These are huge, okay? The probability of A we came up with 4/8, plus the probability of B, which we came up with 4/8, minus the probability of A and B, which is 1/8. 4 plus 4 is 8, minus 1, 7/8. So this is money right here. Love that. Okay? Again, that multiplication part that we tried for here that didn't work, that should only be done, only if you are given the probability of A in a problem, not a number, not something for you to figure out like this, 0.30, and the probability of B would be 0.20, and what's the probability of both of them happening? Okay, and then we're going to get further on, but I would avoid this part if you can. That would be a last resort. You don't need to do that here, so don't do it.